Thank you, everybody, for joining us for this roundtable panel discussion on the state of the art of the hydrogen challenge. My name is Perez. I'm going to moderate this session with the help of these gentlemen. We have 9 people here and 1 more remote. We're going to do our best to try and answer questions and address concerns regarding applications in the hydrogen, in the area of hydrogen valve applications. So I look forward to hopefully a very lively Q&A. We're going to break this session up into 2 or 3 parts. We're going to start with some introductory material just to set the stage and a basic primer on hydrogen technology as it pertains to valves. And then we are going to have a Q&A. We have some questions prepared, but we hope to we hope that the audience will have enough questions that we don't have to ask all of the questions ourselves. We'll take a brief break to observe or to listen to a presentation on some R&D regarding hydrogen sealing, or sealing for hydrogen applications, that will be presented by Francesco Apuzzo. And then we'll continue with additional Q&A if there's still more questions that need to be answered. So without much further ado, I will start the introduction of the panel. This is gives you an idea of our what we're going to be discussing today. I'll be introducing the panelists, or they'll be introducing themselves, I should say, and I will introduce myself in further detail. We'll talk about hydrogen in the big picture, the colors of hydrogen, hydrogen supply chain, key technologies, properties and precautions, and the implications for industrial valves. So I will. This is our panel of experts. My name is Perez. I am a valve consultant. I have over 25 years of valve experience and expertise. My background is in engineering and technology development. I worked for a major valve manufacturer for over 20 years. And so this is where my background comes from. I have some knowledge of hydrogen applications, but I am more specifically a valve specialist. Tom, if you can hear me, and hopefully this technology is going to work, we're going to let you start off by introducing yourself, and I'm going to ask each of the panelists to introduce themselves over the next, take 20 or 30 seconds to introduce yourself similarly to what I just did. Can you hear me?
Thank you, Gil. Good morning. My name is Tom Witte with the Witte Engineered Gases. I've been in the industrial gas business as an engineer for 40 years, designing and installing hydrogen systems, both liquid and gas. So I'm more of a systems engineer, end user of the valves. So that's my expertise. Thank you.
Thank you, Tom. And we're going to just go across the panel.
Yes, my name is Greg Peterson. Good morning. I'm with MRC Global. I'm Vice President of Valves, Actuation, Measurement, and Instrumentation for North America. I work on developing our strategy, go-to-market strategy from a brand perspective, from a product scope perspective. Also support our major end users, including the IOCs, from an AML perspective, which brands they will approve and keep on their AMLs. MRC has a large presence in the quality assessment space, so we support that as well. So good morning, and thank you for being here.
Good morning. My name is Pierangelo Scaglia. I am Vice President Engineering of OMB Group. And also in charge in R&D department. In the last years, I work very deep on the liquid hydrogen valves that it has been developed in the group.
Thank you. Good morning, everybody. My name is Geleijns. I'm from Cameroon within SLB, better known under the name Schlumberger previously. My current role is Energy Transition Technologies Manager. Within, I look after all what I call the green stuff, so hydrogen, CO2, biofuels, geothermal, etc. And in that role, I'm making sure that we have the right valve technologies available for those services, including hydrogen. Thank you.
Yeah, good morning. My name is Wojciech Zmudzinski. I work for BP based in Houston. I work as an engineering advisor for valves. Been with BP for a few years, but in industry for 30 years, I was reminded earlier. Ron, you're gonna beat me by a decade, probably at least. Yeah. But looking forward to our discussion.
Hi, I'm Ron Merrick. I was the Fluor valve specialist and piping and valve SME for globally. I have 45 years with Fluor and slightly more than that with the industry. And I'm going to conferences and enjoying talking and listening to people.
Good morning. My name is Edgar. I'm an engineering manager for Cameron SLB. I have global product responsibility. I oversee product development and research and development activities for our products. I'm heavily involved in API and ISO standards development. So a lot of the standards that we build our valves to, I'm on the work groups. Have been with Cameron SLB for 24 years and in the oil and gas industry for 34 years.
Good morning. My name is Glen Beal. I'm with MRC Global. I'm a SME for piping and valves. I've been in the industry for 40 years. I worked for a large chemical company for 30 years and been with MRC in the recent past.
Good morning. My name is Ray Bishop. I'm with CB&I, who's owned by McDermott International. McDermott and CB&I focus on the storage and the handling facilities of low-temp cryogenic. I've been in the industry for 31 years, so I guess I'm the inexperienced one up here. Nice to meet you all. See you all here this morning.
Thank you. Good morning. My name is Carsten Thoegersen. I'm by the Actuation Technology Division of Emerson. I've been in oil and gas for 30 years and with 25 years focused on the on-off valve market. I've been dealing with the subsea functional safety and the last, let's say, 4 or 5 years I've been looking at the energy transition and the S&D market. So, good morning.
Thank you all. So as you can see, we have a very broad and diverse panel of experts coming from different parts of the industry, different areas of expertise. And this is probably the biggest panel at the show. And the reason for that is, as you will see in a moment, the breadth of the subject we're about to cover. It's extremely broad. It's probably impossible to master the entire subject. And therefore, we need different perspectives and different points of view and different experiences to be able to have a more complete picture. In terms of the big picture, there's an urgent need and a growing need for green fuel sources. That's what's driving the current surge in hydrogen. Hydrogen production, transportation, distribution, and usage is going to see enormous growth over the coming decades. And there's a very broad range of service requirements, technologies, operating conditions, risk profiles, technology readiness, operating experience, etc. As a panel, as we were preparing to have this event, we asked ourselves a series of questions, and these are just some of them. Where is it heading? Where is the industry heading? What are the key challenges? What's the state of the technology readiness? What are the key risks? How are we addressing these risks? How confident are we about addressing them? What's the tolerance for risk, and how are we sharing those risks between the various players in the industry? And how does all of this impact the industrial valve market? Obviously, that's why we're here. To get a broad perspective of it, I think most people have seen some version of this graphic. We won't go into the details of it because I'm hoping people have seen something along these lines before. But basically, there are multiple colors, and I'm sure I haven't covered all of the ones that are out there. But this is intended to describe the various levels of hydrogen in terms of application, in terms of energy source, in terms of feedstock, and in terms of its greenhouse gas footprint or environmental footprint. It again depicts a very broad range of applications. These terms are shorthand for a bundle of characteristics, and these colors have really no bearing particularly on the valves that we're going to be talking about, because within each of them there could be a range of valve conditions that apply to valve application. But it gives you a general idea. I think I would probably be not incorrect to say the majority of these, the majority of production comes out of SMR production of hydrogen, which requires some carbon capture as well in order to achieve the green goal. And that brings in other valve applications than just hydrogen as well. Here again, to depict the breadth of the challenge is a pictorial of the hydrogen supply chain, all the way from the various sources of production through transportation and ultimately to end use. And in pretty much every one of these squares, valves are involved. And each one of these squares has different considerations. So once again, it's broad, it's complex. The valves are used in every area. There are many conditions, many applications, and the technical requirements are quite varied. Next, let's talk a little bit about the properties of hydrogen and what makes it a little bit different. It's colorless, odorless, tasteless, non-irritating. It's environmentally benign, although maybe some people would argue that point. It's extremely buoyant, low viscosity, which represents some interesting challenges. It's highly flammable. That's probably one of the biggest concerns. It's got a low ignition energy requirement. High thermal conductivity. It's got an affinity for oxygen. It has a very dramatic effect on materials, which also is a very interesting challenge. And in the liquid cryogenic state, it's extremely cold. It's one of the coldest elements, pretty much the coldest, and almost. And these considerations have also very important impacts on design. In terms of precautions, I mentioned the flammability, so explosion and fire are critical. Asphyxiation is a risk, and as I mentioned, metal embrittlement. Again, all things that need to be considered when looking at valve design and valve selection. Additionally, when you look at the liquid hydrogen or cryogenic hydrogen case, there are additional factors like fog and impacts on visibility, oxygen-enriched liquid air, which increases flammability and explosion risks. The exposure to extreme cold can be quite dangerous, quite hazardous. Cold gaseous hydrogen can be low to the ground, and so it may not be so easy to see, but it collects in low points in large areas, and that represents a risk as well from a safety point of view. It has, at boiling point, liquid hydrogen. All other gases are liquid other than helium, and so it has a tendency to freeze a lot of things around it if it escapes. And it has one of the highest expansion ratios of any cryogen. One volume of liquid will expand to 848 times the volume in gas. So there again, you have some considerations. When it comes to the range of size classes and applications temperature-wise, this is an attempt at mapping the various sizes relative to temperature and pressure. As you get higher up in pressure and temperature, higher up in pressure, the sizes are lowered down. You can get typically valves up to 8 inches, and in some cases, increasingly, applications are going all the way up to, I believe, 20 inches, if I'm not mistaken, in some cases. So again, in terms of the considerations, there's obviously pressure, temperature, line size. There's the fluid composition and its purity, the concern for safety, which is very much linked to where it is, and what safety risk it represents to people and to property in its vicinity, and of course the risk tolerance that owners have of what may happen if things don't work out. So in terms of implications for valves, it requires attention to design, but it also requires attention to testing and qualification. And in my experience, I would say that is one of the challenges right now that is being faced. Work is being progressed in that area, and so qualification of design is an important factor that needs to be addressed in certain cases for hydrogen. Sealing and fugitive emissions, the question of what are the requirements for sealing and how do we guard against fugitive emissions? And fugitive emissions in this context is more generic than what most people think of as greenhouse gases and VOCs, but general escape from the pressure boundary of the valve is a concern, of course, simply because of the safety risks, among others. The cleanliness requirements is a factor, and there are some things we could talk about there in terms of making sure that it's clean enough without over-specifying cleanliness requirements. Material selection is critical because of the impact hydrogen has on material properties, in particular on embrittlement and risk of rupture. And obviously mechanical integrity is a standard consideration as well in terms of what we need to make sure we look for in terms of valve design. In terms of the outlook, generally speaking, end users, manufacturers, and engineers are rapidly adapting to the special needs of hydrogen in established and emerging applications. That means that in the absence of, in some cases, extensive experience, people are still finding ways to adapt their existing knowledge in a safe manner to develop the right product for the right application. Standards exist for established applications, but there are gaps, as I mentioned a moment ago, for emerging technologies and applications. And one of those, for example, is cryogenic testing. And I happen to be involved in developing standards for cryogenic testing of cryogenic valves for hydrogen applications. And so I'm cognizant of the fact that there's a gap in the knowledge and information in terms of what's out there, what people are doing. There are differences, there are parallel paths being taken, and so there's a need to coalesce around it and come up with a coherent set of requirements that everybody can work with. There are many emerging technologies and applications. You will, as I mentioned, a very broad range of temperatures and pressures and conditions, and so there's going to be multiple standards that are going to have to come out to help guide that. And I guess in closing, the need for new valve designs and for to address the specialized needs, things like relief devices, venting, etc., will drive development and innovation for years to come. So we see a lot of dynamic evolution and development coming up in the years to come in valve applications for hydrogen. With that, I'm closing the general comments. Like I said, it's a primer. I wanted to make sure everybody had a sense that this is a broad subject, and so there's no shortage of things to talk about and ask questions about. So I will start the process of asking those questions. Just give me one moment. Okay. So what we're going to do now, I'm going to open the floor, but before opening the floor, I'm going to just ask a couple of questions of our panel, just to give you a sense of the idea. And then I invite anybody on the floor who has questions, who would like to ask questions, things that are on their mind, either based on what I've presented or based on your own knowledge or lack of knowledge. If you have questions for the panel, please feel free to raise your hand and ask questions. So I'm going to start off by throwing this question out to the panel at large and ask for a response from as many of you as you would like to respond. Valves have been installed in hydrogen pipelines for ages. What's changing now due to the properties of hydrogen in pipeline applications that's driving the need for changes in valve requirements?
I can take a first shot at that question probably. The way I see it, that hydrogen has been around longer than we all exist over here, has been on the earth for a while. and we have been processing, producing, transporting hydrogen for ages as well. So I don't see a change over there. What I do see a change is that the pipeline sizes for the transport, they will increase. The pressure at some points will increase as well. And also the location of the valves will be more and more critical because it can run through cities or whatsoever. So I think that's where the need is, that there needs to be an increased awareness of the potential risk of hydrogen. And therefore there is a need for specifications that set those requirements. I think a lot of end users are writing, as we speak, their valve specifications to write in those requirements as well, to make sure that there is that we meet the minimum needs for those requirements for valves.
I guess I'll jump in, maybe a little bit outside of the valve design, but the economics, right, of hydrogen. Hydrogen has to compete with current energy sources, and that's a big challenge. So I think it's a bit of a balancing act between trying to get to a price point on hydrogen without compromising safety, without compromising reliability. Therefore, we have larger sizes of pipelines, transportation pipelines, challenges with transportation, making that economical, and all the other safety issues that we have with large quantities of hydrogen all of a sudden in pipeline networks. To make it economical, we have to get into repurposing existing pipelines. We can't think that we can build a new network of pipelines and actually make this work. So it's a transition, and I think that's one of the other challenges that maybe we didn't have in the past.
Yeah, I see this as expansion as much as anything else, because we've had hydrogen, hot hydrogen, used in chemical processing, hydrocarbon processing, for a very long time. All the end users have one type or another of metallurgy choices and NDE choices for valves and for piping to handle the increased permeability of hydrogen. Documents like the Nelson curve have been in existence for a very long time. So those, as we talk through these new standards, these guys are pretty much, you guys need to do something, and our part with the hot hydrogen, we're in pretty good shape. Where the technology comes is distribution primarily, as opposed, I've lived in Houston. It's not that unusual to see a hydrogen truck going down the freeway. But to transport the volumes that we can really use, that really has a lot of solutions that are not yet fully developed, and that's really where we are.
Yeah, thank you. And just to add to that, as Wojciech and Ron said, I think as the existing infrastructure that we're used to using natural gas, all of these operators are going to start blending hydrogen into the natural gas as well as a means of transport. And there's a lot of questions around what does that blending do to the natural gas at its ultimate destination, and to the pipeline structure itself, and how does that affect the valves? So that's what we're trying to attempt to address with some of the existing standards that we're writing, and start helping the operators understand the implications for existing valves, for legacy valves, and also for new valves as well.
I guess I'd like to add that as piping spec engineers and writing your piping specs to recognize and be cautious, because if we have a spec and we had hydrogen specs around forever, looking at 6-inch, and now I need to go up to 16-inch. When it comes to the valve, you need to use caution and not make the assumption that your spec can just be expanded, not looking at wall thickness and all that, but from the valve design, you need confirmation from the valve manufacturers that what I'm writing and what I'm specifying is indeed appropriate as I go from 6 to 16-inch.
Yes, and I would add, based upon the economics, that that the previous panelists have stated. On the storage side, again, we're getting bigger and more production, more throughput for shipping. You know, the shipping industry to import hydrogen to the areas of the world that, you know, don't have a readily available fuel source, or converting from natural gas, LNG, to liquid hydrogen. So to make all the economics work, storage quantities and throughputs have to increase drastically. Like in some cases, go from a 5,000 cubic meter a sphere to a 40,000. So that's the scale we're talking about on the storage side.
Thank you. I'm not sure I can add a lot from a control and actuation point of view, but what we do see is that I normally say an actuator is an actuator, whether it's in one industry or the other. The requirements we see within hydrogen is probably in the blending, as Ed was saying. Do we see 5%, 10%, or 15%, or do we push the boundaries a bit more? Because if we use the nitrogen or the gas as a media of driving our control, our actuation, then that's an issue. We don't, like I said, see special requirements. We do that in relation to explosion proof, but that's one thing. The other thing is, what would it do to our equipment if used in, let's say, 20 or 25%?
I want to follow on with that because we maybe missed, I don't know if you gentlemen want to say more. I do have a question for Pierangelo from a cryogenic standpoint, following on this question, because I would like to hear if you have any insights in that context. So again, the question is, what's different, what's changing in terms of demand on valve requirements for cryogenic case?
Yes, first of all, it's necessary to split the valves from cryogenic and standard temperature and high temperature. First of all, you have to consider that for high temperature there are some already in place some specification like API 941 or ASME 1312. For the more standard temperature, there is a big job almost at the end, I think, due to the API 6D Annex M. And for the cryogenic, we have some problem. Okay. Anyway, I will try to start with the type of valve before. Type of valve in cryogenic application, typically until now, the typical valve, it has been a globe valve. And this is due to the fact that until now, the request of this type of valve was generated only by aerospace, generally speaking, very few other requests. So the dimension are always very small, 2, 3, 4 inches maximum. And now the request start to be to increase, and we have already seen a request about 6 to 8 inches. And in the future, in the near future, probably this year, there are some big projects in Far East, like in Japan, where the request is for valve up to 24, 26 inches. And the valve selected are ball valves. Ball valves, why ball valves? Ball valves because to move this big quantity of liquid hydrogen, they don't want to use, it's almost impossible to use a globe due to the fact that the fluidodynamic characteristics are very, very low. The CV is very low. And this means that instead to use maybe 24 inches, probably they have to use 36 inches. That is incredible bigger. And butterfly also, they have some problem. And they have select ball valve. So the two typical valve that now seems that is request for liquid hydrogen is this type of valve. The other point is the specification, qualification, test, and specification to design the valve. For the design at the moment, there is no specification. For the qualification test, we are working on MSS. We are a good point now. I think that before the end of the year will be released at least one specification for qualify the valve. And this is the first step probably to have something that gives some indication about the qualification of this one. That is not very simple, frankly speaking, because to test the valve at minus 253, minus 254 is not very simple. It's almost impossible to use liquid helium, not because due to the cost, because until you test the valve, a small valve like half inches, 1 inch, probably it's possible to use the standard procedure with submersion. But the cost of the helium, the liquid helium, and also the fact that it's not very easy to find the liquid helium around the world in this period, and practically is the cost of to test a valve 6 inches, 8 inches should be impossible. So there are other systems that the MSS define to test the valve up to 20 inches, maybe.
Hopefully.
Okay. And this is the point. The critical point at the moment is that there is no specification regarding the structural calculation of this valve or thermal calculation of this valve, and this is a big hole at the moment. Is a big hole.
And I've got to say, Tom, who is joined with us remotely, has been kind enough to wake up at 4 o'clock in the morning his time. So I'd be remiss if I didn't at least offer you, Tom, a chance to respond from your perspective and as a specialist in cryogenic hydrogen. How do you see things evolving and differing from where they have been so far, if I may put you on the spot with this question?
Yes, hi, Gil. Yeah, there's a couple areas that are have to be addressed in the use of hydrogen. One's cryogenic and one's really the high pressure applications. So the cryogenic valves have been around for many years, mostly smaller flow valves. But there is one particular valve that needs to be developed, and that's a valve that will keep the liquid hydrogen system from needing purging. That's a big problem when you're delivering liquid hydrogen. The pipelines you're delivering into can have no air in them. So they have to be purged, and there's a lot of loss involved and a lot of time involved in doing that. Currently, there's a valve for high pressure gaseous hydrogen that will allow connection and disconnection without adding air to the system. That needs to be developed for liquid hydrogen. Is being looked at globally fairly at a very high level to make sure that does occur. That's one issue. The other issue is where we're seeing newer applications is in the high pressure area. It keeps growing. You know, it started at 350 bar for filling vehicles. Then it went to the 700 bar because of trying to get more hydrogen fuel available for longer distance travel. Some of the valves that have been used have been the wrong type. There was an incident in the US where it appears that ball valves were used during transport, and during a fire, the valves actually melted the seats and the valves opened, adding to the fire. So how these valves are applied for both gas and liquid is very important in future development. Thank you.
Thank you very much, Tom. Based on what everybody has heard so far, are there any follow-on questions that anyone would like to ask related to this particular theme? In other words, what's new about hydrogen, or what's different, or where do we need to go? If not, I have more questions we can continue with. Yes, please. Let's make sure we get a mic to you here.
Okay, Mark Goodfellow from Elderly Systems. One of the main product areas we work in is metering, and we see lots of hydrogen metering requirements. Not many orders at the moment, but lots of feeds and studies. And one of the issues we grapple with is hydrogen is, and we're normally talking about metering gaseous hydrogen, but one of the issues we grapple with is what's the maximum allowable line velocity in a gaseous hydrogen line, because it's not abundantly clear. Everybody seems to reference the erosional velocity of a pipe, and we sit there on the receiving end and we're not quite sure what's right or wrong. Because it's less dense, in theory you can run it at a higher velocity. The flow meters we deal with will handle that, but you then wonder, is that a good idea or not? So I don't know whether anybody has any thoughts on that, but I'd be interested.
Does anybody here have an answer or a qualified answer for that? An opinion, general guidelines?
Yeah, we are also in the storage facilities. We're seeing and allowing higher velocity, but to put a number on it, no, we're debating that as well in our studies. So I don't think there's a fixed number out there, but yes, we are pushing the velocities up. So I don't know if that really answers your questions, but other than says we're pushing the velocities in the pipelines or in our studies that we're doing.
Okay, that confirms we're in the unknown country then.
Yeah, we're in unknown territory. Well, let me throw the question again to Tom. Not again to put you on the spot, Tom, but from your perspective in the applications you're involved in, do you have guidance or guidelines that might be relevant to the question in terms of line velocity?
Gil, I'm having a hard time hearing. I had a hard time hearing the question. Could you just repeat the summary of what was asked?
Oh, in summary, the question was basically in transport, line velocity is a question whether or not it's possible to tolerate higher line velocities when sizing piping for hydrogen transport in the gaseous state now, right? That's the question, yes. So basically, what guidance might you know of in that regard?
Yeah, hydrogen's not like oxygen. There's velocity limits with oxygen because of potential to ignite the pipeline. The issues with hydrogen are mainly due to pressure drop in velocities. So you're limited by how much pressure drop and the diameter of the piping that you're running, and that's really the driver, is the pressure drop in the piping when you look at how high velocity you can get to.
Does that help answer your question, at least directionally?
Directionally, yeah.
Yes, okay. We're not a consulting service, by the way.
Oh, I understand that.
All right. I'll move on to another question. Is there another comment? Tom is, well, yeah, but this panel isn't serving a consulting role right now. Yeah. Okay. Okay. Another question. This is to compare hydrogen service to natural gas. So how do operating conditions for... Oh, is there another question? I'm sorry. Please.
Sorry. So we've noticed in pressure equipment for hydrogen service that there are some issues of impingement and areas with higher turbulence and impingement seem to have a deeper penetration of the hydrogen molecule into the steel network. So I think there may actually be some lab type work that would be appropriate on the velocity question and turbulence and impingement.
That's very interesting. So velocity is not strictly related to sort of the macro level of delta P in the system, but also its effect on the material properties due to the impingement of the hydrogen molecule into the material itself. Okay, that's very interesting. And does that lead to any limitations on velocity that you're aware of?
I don't think we've learned enough. There's also some probably some contaminant issues that contribute, but we've certainly seen enhanced blistering and hick cracking in areas of impingement.
Very interesting. Thank you. You're supposed to be asking questions, not answering them. But that's okay. We appreciate it. Okay, so I was going to ask a question with regard to comparison between hydrogen and natural gas. What are the key challenges for pipeline valves in hydrogen service that differ from natural gas service, and how do operating conditions for hydrogen pipeline service differ from natural gas?
That's a good question, and especially there is a specification coming out, API 6D Annex M, that addresses most of those issues. So the challenges we see, well, first of all, is an extremely small molecule, obviously, and then the high flammability. I think that's in a summary of what it is. But if you go a little bit further in that, because of the small molecule, it can penetrate metallic materials, what you just mentioned, and more in an atomic form. And so hydrogen embrittlement, that's a concern. Another concern is that it can also permeate soft materials and change the mechanical characteristics. And it's not something that immediate, it can happen over time, and that's why it's important to have design validation to make sure that the materials that we are using in a valve will be suitable over time. If you have hydrogen molecules that can enter the soft materials, it changes the mechanical characteristics, and therefore the sealing behavior of that valve, that will have an effect on that. Or even it can go as far as explosive decompression, where you will permanently destroy the seals. Other topics are leakage, because obviously it's more difficult for seals to retain that smaller molecule. So internal leakage leads to potential loss of product, and the end users are typically not happy with that. Or even worse, put at risk the downstream work of that valve that would be leaking. External leakage leads to fugitive emissions. On itself, it's not a greenhouse gas, but it's considered as an indirect greenhouse gas because it retains the methane longer in the atmosphere. But more importantly, if you link that together with this high flammability of hydrogen, it gives more higher exposure to positive fire and explosion risks. So I think those are really the main challenges for valves in hydrogen services. Wants to add something?
Some more comment on that? That was a pretty good answer. It's pretty comprehensive. Good summary for sure. Thank you. Any follow-on question to that? Again, distinguishing or contrasting natural gas service to hydrogen service. Does anybody have any follow-on question to that? I'll take that as a no. Let's see, where are we at? This is a more straightforward question. In blended fluids containing hydrogen, what percentage of hydrogen constitutes hydrogen service? And how do the different concentrations of hydrogen impact valve design selection and specification? We did talk a little bit ago about different levels and concentrations of hydrogen, so hopefully the mic's got to go on, I think.
There we go. Yes. In the classic hydrogen piping schemes for processing, somewhere around 75 psi for a 5 bar. Because in previous studies, going back to the 1940s, there was a lot of issue about hydrogen permeation and whatnot. Those numbers are probably not good enough anymore. But we used to just arbitrarily classify that if it was greater than 5 bar, poof, it's hydrogen service. If not, then it's a regular hydrocarbon. And those numbers probably were good 50 years ago. I would say we at the very least ought to revisit those in terms of where we see significant permeation starting to happen, where we see significant embrittlement starting to happen, and the issues of HIC and SOHIC and pipeline service, of course, are very prominent. So if we're going to be doing this for real, sending large quantities of hydrogen through piping, those are answers that we need, and not sure we have really good ones yet.
Thank you. Anybody else on the panel able to comment on this? No? Okay. All right.
Gil, just a
Please,
quick one. So API 500, right, from an area classification point of view, defines anything above 30% hydrogen as hydrogen service, right? So it's not on a molecular or material compatibility perspective, but it's more, is it now classified as, potential for explosion, right? So that's one way to think about what is hydrogen service, what is not, right? Just from that one perspective. And there's others, of course.
Okay, that's one angle to consider, one aspect to consider in defining the hydrogen service. Okay, very good. Any follow-on question to that? Okay. Let's see. Let's go to this. Okay. Standards for the testing and qualification of valves for hydrogen service are in development at various standards organizations. That includes ISO, API, MSS. What are some of the key parameters with respect to testing methods, testing media, acceptance criteria, etc., that should be considered in developing these standards, and what is the state of the art in the qualification of valves for hydrogen service? And I'll add to that that we have to consider the broad range of cryogenic all the way up to high temperature. So I'm able to answer some of that, but does anybody want to get started on some of that before I say anything? Because you fellows have been you're leading the way in terms of hydrogen standard.
Yeah, well, API 6D, we wrote a new Annex M. Jonathan and I finished up work on it this morning. It is literally in our inboxes to return to API for publication. So we do expect that in a few weeks, but we only are focused on hydrogen gas service in this. So we're specifically not addressing cryogenics or high temperature. We opted, well, for a few things. First off, we have testing in there for fugitive emissions as a mandatory requirement, both for qualification of the valve and for production testing. For the production test, we did add, in the document, we've added the use of forming gas, which is 5% hydrogen, 95% nitrogen, for the production test. We did not feel the need to add forming gas for the ISO 15848-1 qualification testing. We felt that any existing qualification test, if it was tested with helium, would be a suitable certificate, so we didn't feel that that was necessary to redo. But we left the main testing with adjusted acceptance criteria. We left the 6D testing as gas testing with nitrogen. We didn't feel that we should be testing with helium because of the scarcity of helium as a natural resource. We didn't think that that was, as a standards development organization, we didn't feel that that was a smart thing to do as a good steward of the product available on the planet. And it's more difficult to obtain and more costly of a test. So we standardized on testing with nitrogen, but we adjusted the acceptance criteria to replicate the leakability of nitrogen to help it replicate what a test for hydrogen would be. So that's one thing that we've done. We did address testing for non-metallic materials. We addressed how to select materials for metallic materials. There's an what I call an easy path and a difficult path. So there are some materials that are restricted in use, and if you want to use those materials, some additional testing needs to be done. If you don't need to use those specialty materials, then you can stick to some standardized materials with no further testing necessary. I do know that MSS is writing a testing-only document on how to test valves for hydrogen service.
That's
I
right.
do believe that that's going to cover the entire range from cryogenics to high temperature.
That's correct. That's the intention.
I'm not sure.
I'm going to comment on that a little bit
Okay,
after.
perfect.
Yes.
Yeah, I'm not sure of their status, but we're ahead of them.
Yes, you are.
So,
Definitely.
So
ahead.
6D, we do expect 6D Annex M, 6D Addendum 2 should be published by July, is what we're anticipating.
Yes, that's great. That's
So.
really good.
Anything to add to that, Jonathan? Jonathan and I are co-chairs of that document. Okay.
Yeah. Yes.
Just a quick question, Ed. The testing durations, are they comparable to the standard they're what is used for API 6D, or are they extended hydrogen, high pressure nitrogen seat test, extended duration?
I think we extended the durations
Yes.
too, right? We doubled the duration,
Some
right?
of the duration, yeah, the duration.
So we doubled durations and also modified acceptance criteria.
Okay. Do you think that is enough?
Yes.
Yeah, if may I want to expand a little bit, the reason for that is that it takes typically twice the time for nitrogen to be detected as opposed to hydrogen. So that's the reason why we have twice the test duration. And acceptance criteria is half of it, well, almost for that same reason, because, well, you need to be tight against hydrogen and not against nitrogen. So that was a reason behind it. But this is not a 5-minute discussion. This took quite some time with the whole work group in order to come to a conclusion.
I expected that it would be a longer duration. I was just curious to what, and maybe how you came to a determination. So
Yeah, it was
very important
lengthy
topic.
discussion, multiple times.
Right.
and yeah, in essence, it's double the duration, half the criteria, half the acceptance.
You know, coming
60.
to this from a distributor perspective, where we could be holding valves, you know, we'll be watching to see the testing requirements develop as the valve technology, as the valve requirements develop. We'll be watching the testing. We do, you know, can the manufacturers do this testing at the factory level? Can they do that economically? You know, with the extended duration, or do we assume some of that testing responsibility at the distributor level? Is there a product that can cross over from, let's just say, natural gas to hydrogen service, depending on the level of criticality? And then, so do we apply high pressure nitrogen seat test at our level, or is that done at the factory level? So we'll be watching all that and then developing our business model to fit.
Sure. And just to follow that up with a quick summary, a good way to understand how we developed the hydrogen annex in 6D. If you're familiar with the quality specification level, the QSL levels in 6D, we sort of paralleled that with a hydrogen specification level. So as you increase in the hydrogen specification level, you add on more testing. So some of that testing I envision could be done at a third party or an aftermarket place, but not all the way up to the highest level. At the highest level, the testing must be done at the factories. But some of the testing at the lower levels, I could see may be able to be done at a third party post manufacture.
Right. Okay. One of the I don't know if it's a trick question
Greg,
or
go
not.
sit out there.
Who determines the QSL level?
The purchaser.
Thank you. That's the trick question, is he determines. So no regulations, nothing driving that. I mean, it certainly has guardrails, but
Sure. And even on the development group, many end users were participating, and they themselves said, we will develop our specification based on our own risk profile and how they view their own risks. So one end user may, for the exact same service, may opt for a higher specification level of the valve than another end user may.
so yeah, that's my thinking around that, is if you have someone that's building assets for hydrogen service, and he's gonna build this asset and then sell it, or someone that's gonna own and operate, could take two different approaches to the.
Correct.
Yeah.
Correct.
Good discussion. Tom, I wanted to ask you on the cryogenics side, because you are participating in the task group as well with me and others in developing the cryogenic testing requirements. I wanted to ask you if you could give us some insights from your perspective on how valves traditionally have been tested for cryogenic hydrogen service. What kind of temperatures, what kind of pressures, what kind of durations, what kind of acceptance criteria are you familiar with and that are commonplace in your experience?
In the test temperatures for most of the valves are usually using liquid nitrogen. Helium, as was said earlier, is very difficult to get, besides being very expensive. And not only that, it's very difficult to maintain a bath of liquid helium. So in most cases, the testing, as I understand it, has been done by liquid nitrogen. Again, I'm an end user of these valves, so I'm not testing them. I'm just understanding what the manufacturers are typically putting these valves through. And these are, again, smaller valves. These aren't the larger valves. These are usually 2 inches and below.
Very good. I had a deliberate intention in asking you this question because, as you know, we're grappling with this same question with the intention of it being applied to larger sizes, and we've been debating what is an appropriate temperature, and it connects to another topic that hopefully we'll get a question in on later, which is how can I put it, liability. Making sure that the gap between that liquid nitrogen and liquid hydrogen, that's a pretty big temperature gap, and material changes in that temperature, material properties, I should say, change in that range. Behaviors change in terms of both mechanical behavior and metallurgical behavior. And so I think there are challenges as far as closing that confidence gap at testing at the higher temperature versus operating at the lower temperature. And I just wanted to sort of share my own perspective on developing the cryogenic testing standards. So as was mentioned, I am vice chairing on the Manufacturing Standardization Society for Piping and Valves in the US in developing testing standards for valves and hydrogen service. My particular focus is on the cryogenic side, and the chair, Greg Johnson of United Valves, is the overall chair, and he's focused on the gaseous hydrogen testing requirements. So in the cryogenic domain, we are focusing right now on developing I'm starting with the kernel being the type test, the type qualification testing, the one-off. You test a family of valves to this particular qualification. And in that case, our intention is to bring the test down to pretty much liquid hydrogen temperature, so minus 253, 254, give or take, and use criteria that are, in terms of leak allowable leak rates, in line order of magnitude with existing cryogenic testing standards. So there's likely to be an alignment with existing leakage criteria. When it comes to production testing, we're going to definitely have to put some significant amounts of water in our wine. It's not going to be practical to get that type of temperature. It's just economically unfeasible, and the processes required to get to those temperatures they're not commercially viable at volume. But one of the other things that we're focused on is making sure that we have flexibility in the testing methods, and we're looking at least 3 different testing methods, one being immersion, which is the most common use case, one which would be using a cryocooler or an external refrigerant that it conducts the heat away from the valve, and the third is a flow-through method, which is also being seen in use. So the 3 different methods that we're going to look at, and we're going to be trying to make sure that the criteria we put in place are going to be comparable. In other words, that there is going to be like-for-like results when we get performance out of the test. What else can I say about it? So we're focusing first on the type testing, then we'll go into the production testing, and ultimately we'll marry the entire thing. We're probably, I'm going to guess, a year away from where we could probably publish, and we may end up publishing in 2 sections, depending on where everybody is. If we happen to be making better progress on gaseous, we'll do that, and then attack on the cryogenic later, or vice versa. Or if we're fortunate and can put it all together, we'll put it all together. But you guys, on 60, you're very much ahead of us in that regard. And the reason for doing all of this is because there's a clear lack of standards, particularly focused on the cryogenic case. And there's a need to be able to establish some level of confidence in the performance of a cryogenic valve at those conditions for a hydrogen application. I think.
I have one more question for Ed, if I could. So coming from a manufacturer perspective, you see the valves going into hydrogen applications I know some of the valves are the same valve that would be in, say, a natural gas application. Will you, or have you decided as a manufacturer, will you be doing the more severe test so that the valve can go into both services, or do you think you'll wait and see what the customer specifies, or?
Jonathan's actually in charge of that.
Okay,
group
I got you.
within
Maybe I asked-
Cameron, so let me let him address that. For
Okay.
Yeah, I think that's a good one. Ideally, we would qualify everything to the highest standard, obviously, but it has a cost. It has a cost and also a lead time because it's a destructive test. There is a lot of cycling involved, and if you look at pipeline valves, that can go up to 48 inch, even larger than that. So there's a cost involved. So what we would like to do is get more feedback from the industry. Just let's get the standard out there, and that's why we wanted to have the standard out there early enough. Let the operators think, okay, what is the likelihood of severity, of the criticality of the valve? And then if possible, well, pre-qualify the valve standard to those that are mostly expected, and to the highest as well. And it can also depend, maybe the smaller valves at the higher pressure classes are the higher levels, and the bigger sizes, the lower levels. We still don't know. There's so much unknown in the industry, and that's now as well for the end operators as well, end users as well. So that needs to be discussed and needs to be discovered. But that's the interesting market of hydrogen, in my opinion. Yeah.
Still evolving.
Oh, yes.
Maybe I'll add to that a little bit, right? So from the end user's perspective, because this is such a relatively new area, right, for a lot of us, looking at it from risk perspective, right, we have a little recommendation or a few steps in API 6D, Annex M, sort of at the beginning about HSL levels, so maybe they'll be called SLH levels. You'll hear both. And that's gonna kind of guide us a little bit on what qualification, what testing, marking, documentation requirements. It's aligned, as we said, with QSL levels. The qualification. So some of the projects, as I said at the beginning, some of the projects that we're working, for example, can only go into the sort of, serious phases, right, of the project if the technology level achieves a certain level, right? You cannot go in with a TRL2 or TRL1, right? You have to be certain that you're starting off with, let's say, at least 3 or 4, right? That's the challenge, right, is do we get there by qualification? So we just go and say Annex M, which is a modification of Annex F. Many of you are going to be familiar. And is that good enough? Are we comfortable with that? Or do we take advantage of potentially some valves that have been out there for a few decades, right? Maybe not a 36-inch valve, but maybe it's a 12-inch or 6-inch. And that brings us to that technology level that we're comfortable, right? So we're saying, okay, that's we can proceed with that project, right? It makes it viable. You don't have to spend time, money as well, but also time to get to a comfort level, right? To this technology level that you require, and that's kind of the question at the moment, right? So it's not just okay. Well, we'll qualify to Annex M. We're good to go. These are now, valves that are absolutely, fit for service, proven to go in for 25 years. It just doesn't work like that. Yeah.
I guess I have a follow-on question that's part of our prepared questions that connects to what you're saying, and if you could perhaps elaborate on it, I'd appreciate it. So there's the broad range of applications, there's the risks associated with the broad range of applications, and there's a gap. There are gaps, and there's the concern that who owns the risk? How does that risk get shared? How does it get managed? How are we seeing the industry deal with the differences? Like, okay, sell me a valve or supply me a valve that you've tested to minus 196, but run it at 253, and you own that problem. How are you seeing, and I'm obviously giving you the cryogenic case, but there are probably similarities in other applications. How does the panel, or how do you, Wojciech, see this question being addressed? What are the practical implications, and how are people navigating through that?
Yeah, I guess, the key thing is, right, that the ownership of risk is always with the owner operator, right? So we have to not just own it, but manage that risk, right? It's all about understanding what the risk is and managing the risk. Sometimes managing the risk means we just cannot go and do certain things, right? We have to stop and do something else, or stop and do maintenance, do replacement, or what have you. Sometimes we assess the risk and we say we have enough, enough, I guess, mitigations in place to be able to continue, right? But the ownership, the management and ownership of risk, at the end of the day, is with whoever runs the facility, right? Whoever runs the pipeline, who operates the pipeline, owns that risk on a daily basis. And that's no different to what we do today with oil and gas, what we do in power plants, right? At the end of the day, it is your plant, you're running it. Right. The help from suppliers, help from engineering companies, allows us to understand what the risks are, right? And it allows us to, to feed into this sort of risk assessment, right? And then basically come out at the end saying, these are the mitigations. At some point we draw a line, we say, no, we cannot go and proceed with this. We cannot continue with certain thing. At some point we can say, based on the assessment, we have enough mitigations, we have enough management of risk in place that we can continue, right? It's on a case-by-case basis. And this is why, a lot of end users don't have this alignment of quality levels and now HSL levels, or SLH levels, because it's so specific
to their
potentially
case.
To not just the facility, but even a location, right? Talking about hydrogen potential for explosion, right? Detonation, really an explosion. You would think, well, if there's a line, a pipeline, a piping system with valves out in the open, right? Is it the same risk as it's inside of the building? Of course it's not, right? So the one that is outside and let's say next to the loading area where you're loading trucks, is that also because it's out in the open, right? But it turns out that if there's a canopy, if there's a potential for containment of the of hydrogen, it is a special case of it's not in the open necessarily, right?
Yeah.
So you have to assess that location and be very specific. Yeah.
There's a question from the audience. Can we maybe pass the mic down?
I wanted to make a comment around the risk side because, frankly, I don't think the communities are ready. And that worries me. That worries me about whether one of my children will own a house near a dispensing station, because I don't think there's enough control on it in North America. There is a pretty good NFPA standard that requires a community facility risk assessment to be made if you're going to have liquefied natural gas. Is there any equivalent document being generated for hydrogen is a very good question. But even the fact that there is a standard on liquefied natural gas, most jurisdictions have not adopted it. Most jurisdictions have not adopted B31.12. Many jurisdictions haven't adopted B31.3. North America is a bit of a cowboy environment to a large extent as compared to Europe, where there is more dialogue on these topics. But I'm quite worried that the learning curve could be painful, and that today it is possible to license or rent a facility for dispensing hydrogen, and it's a skid mounted, and it can move into a location that is not controlled. Is that a responsible use? Is a very good question. And I've been in the industrial environment, and I had the walls of my building move 7 inches during a vapor cloud event. I don't think a commercial house would survive that.
You bring up an important question considering plans for infrastructure in the United States to basically install a massive amount of infrastructure for both, I guess, electric power stations and hydrogen fueling stations for transport usage that will basically run along the interstate system. And without those safety requirements in place, you're talking about a very high-risk situation because it covers the entire country in the United States. It would be massive. So you bring up a very important point, and I'm certainly not aware of what's being developed in that regard. Are we ready?
Gil?
Yes.
Can you hear me, Gil?
Yeah, Tom, yeah, please. Before closing out the question, I was going to
Yeah,
ask.
the hydrogen stations, there's a number of them in California and a number in the other parts of the country, and they all have been designed for NFPA2 for the most part, along with the fire codes. There are code requirements and permitting requirements for putting any of these stations in that are pretty rigorous. For an overall, there's two methods of managing the risk. One of those is prescriptive based, that's using the actual distance requirements in NFPA2. And then there's performance based, which will allow you to actually do calculations and prove the type of thing you're talking about for LNG. So those codes do exist, and those typically are followed.
Thank you. Very good to know.